Okay, here we have question number 3. So you needed to look at the substance, draw the Lewis structure. You needed to evaluate whether the bonds were polar or nonpolar. And you would have done this by finding the electronegativity difference. You could find the values in the book. Then I wanted you to determine, based on whether it had polar or nonpolar bonds and the Lewis structure, whether the molecule is polar or nonpolar. And from that, you should be able to make your decision on which has the strongest intermolecular force, or what is the strongest intermolecular force present between the same molecules. So the first one, you end up with CS2. This ends up having a structure that looks like this. You find that there is very little electronegativity difference, actually no electronegativity difference between carbon and sulfur, making each of these bonds nonpolar. Because the bonds are nonpolar, there is no way you could have a polar molecule. So the molecule itself is also nonpolar. This is pretty rare for two different elements to have the same electronegativity unless they are the same element. So the strongest London or the strongest intermolecular force present is our London dispersion forces. Then we have carbon tetrachloride. It ends up with this nice tetrahedral structure. The carbon chloride bonds are polar. You end up with an electronegativity difference of 0.5, but because the molecule is symmetrical, the molecule as a whole is nonpolar, meaning that, or because the dipole nature cancels out. So again, all we have are London dispersion forces between molecules of carbon tetrachloride. With ammonia, the structure looks like this. We have 4 things around a center atom, 1 unshared pair, so this is trigonal pyramidal. And the nitrogen-hydrogen bond is quite polar. We end up with a 0.9 as the electronegativity difference between those two atoms. And the molecule itself is polar because it is not symmetrical, so the dipoles do not cancel out. This molecule ends up having hydrogen bonding between ammonia molecules because you have a nitrogen bonded directly to a hydrogen. So this hydrogen here is electron deficient and will seek out other unshared pairs. Methane, we have CH4. It ends up again with a nice tetrahedral arrangement of the atoms. These bonds are very slightly polar, and that's important for you to remember. The CH bond only has an electronegativity difference of 0.4, so even though it's polar, it's just barely polar. And that will come into play when we look at larger molecules, and most of those involve the carbon-hydrogen bond. But because of the tetrahedral arrangement of these atoms, we end up with a non-polar molecule. It is symmetrical, so the dipoles cancel out. And so we only have London dispersion forces between molecules of methane. SO2, its structure, it ends up having to be a resonance structure, so you would have had to draw on both. This is bent, so we've got 3 things around a central atom, but there is 1 unshared pair. And the bonds, the SO bonds, are polar, quite polar. They have a electronegativity difference of 1. And the molecule itself is polar because of this unshared pair on the center atom. It makes the molecule non-symmetrical. So we have a polar molecule, and this would undergo dipole-dipole interactions between molecules of SO2. Water's structure we should be very familiar with, this bent structure with 2 unshared pairs on oxygen. The oxygen-hydrogen bond, again, is very polar. We've got 1.4 electronegativity difference. And the molecule itself is polar because that bent structure is not symmetrical, so the dipoles can't cancel out. We have a hydrogen directly bonded to an oxygen, and so this hydrogen is very electron deficient, so we will have hydrogen bonding between water molecules. PCl3 ends up having a nice trigonal pyramidal structure with an unshared pair on that center atom. The bonds between phosphorus and chlorine are all polar, and you have a polar molecule because it is a non-symmetrical molecule, so the dipoles cannot cancel out. So we would have dipole-dipole interactions. HF, The bond here is a very polar bond. This bleeds over into what we classify as ionic bonds. The attraction, fluorine has a very high electronegativity. This is still classified as a molecule, so we will call it a very polar molecule instead of ionic. Although when we do write the formulas for acids, we do use the charges in writing those. We have polar bonds, and of course it is going to end up being a polar molecule. It only has two things in there, and this is hydrogen bonding. So this hydrogen's very electron deficient and will seek out other unshared pairs. Chlorine gas, we've got two chlorines bonded to each other, so it is a nonpolar bond with an electronegativity difference of 0. So it forms a nonpolar molecule and only has London dispersion forces. SCO ends up looking like this, very similar to the structure we had at the very beginning of this problem. The sulfur-carbon bond is nonpolar and has no electronegativity difference between those atoms, but the CO bond is polar, and quite a bit so. That means that oxygen's going to be pulling on the electrons not only from carbon but also from sulfur, resulting in a polar molecule overall. This would have dipole-dipole interactions. Then the next two problems were just some basic concentration problems. So the first one is a dilution, where we're going to use MCVC equals MdVd. And in most of these problems, at least the realistic ones, you're going to be solving for VC. We want to figure out how much of this concentrated solution we need to prepare of this molarity. So you work the problem this way, and it would be 16.7 milliliters. Be careful with the way the question is worded. I could have asked, how would you prepare this solution? And 16.7 milliliters would not answer that question. You would say that you would need to take 16.7 milliliters and add it to some water that was in a 100 milliliter volumetric flask, and then you would add some more water till the bottom of the meniscus was at that line. That would form your 2 molar solution. Of course, you would want to have water in that volumetric flask before you added the acid, because you always add acid to reduce the chance of having a lab accident. Number 5 is a basic molarity problem, but it does involve a hydrate. So we have copper 2 sulfate pentahydrate. You have to get the molar mass of that. So you're going to find the mass of the copper 2 sulfate and add the mass of 5 waters, resulting in this molar mass. We have molarity and liters. And so you would multiply those together to get your moles, and then use molar mass to convert to grams. If we had 3 sig figs in here, it would be 0.250 grams. I think the way it's actually written, it would end up just being 0.2 grams for the correct number of sig figs.